Good afternoon and welcome back from your break. We'll now continue with the 7th session, New Technical Solutions. And first we will see Dimitris Zafirakis from the University of West Attica in Greece. And he'll make a presentation named Recovering Wind Energy Curtailments in Island Grids Through Water Pump Driven Demand Response. Are you ready, Dimitris?
Yeah, definitely. Thank you very much for the invitation and thanks for the kind introduction. Yeah. I will try to share my screen. Give me a second. Thank you very much.
I would like to thank you and then go to the next in the session 7, Energy Management System for a Smart Prosumer by Shraddha, Shriram, Maslekar and Levente, Tamás, Tóth from Aalborg University in Denmark. Are you ready, both of you?
Yes,
Hi.
Hi.
Yes. We are ready.
Okay. Welcome. Good to see you.
Thank you.
And well, the screen is yours.
Yes.
Thank you.
Thank you.
That's it, yeah. Okay. Can you see it?
Yes, we can.
Okay, super. Then I would like to introduce ourselves. My name is Levente Tóth, and I'm a student at Aalborg University, and I'm currently finishing my master's studies in wind power system specialization. And my colleague is Shraddha, and she's also a master's student, and we are currently writing our master thesis in this exact topic. We would like to thank you to be having us here, and we also would like to thank for Florin, our supervisor, for his guidance and help for whom without this project couldn't be possible. So our project is Energy Management for Household Prosumer, or EMS for short, and this is a very interesting and upcoming topic, and we hope that we can show a brief introduction to this in the upcoming slides. So first of all, we would like to talk about what is a prosumer. I think everyone knows about climate change and how big a problem it is imposing to us, and a lot of blame is going into the energy sector, and but it's also giving us an edge on renewable energies, and big power plants, wind power plants and PV fields are popping up everywhere. And you can see it on a smaller scale on the low voltage network as well. People are installing their own green production, PV panels, rooftop PV panels, small wind turbines, and this new type of production is called a prosumer because it also consumes and products energy as well. And it has numerous advantages for the prosumer. It can have economical advantages as reduced energy bill or other governmental incentives like feed-in tariff or favorable loans to cover your expenses for the installment costs. And also it has environmental effects because it's a green energy. To understand how a prosumer setup looks, we can see the picture on the right side. We considered a house because our literature, going through our literature work, we saw that prosumer models are more popular among people who live in rural areas, like a bit distant from cities. And because of this distance, they usually do not have access to district heating. So they try to solve their heat demands in a different manner. And heat pumps are a new and upcoming technology. And it's really getting really popular among prosumers. And also we are considering future trends. So we considered electrical vehicles for the type of commute between the house and the city or the workplace where they live. These two new load types and the general load, this creates the demand side of our prosumer. And on the generation side, we considered the most two common production units, PV panels and the small wind turbines, which are also only possible on the rural areas, not in the city. And one most important, significant part of the prosumer is some kind of energy storage system. which can serve as a buffer between the demand and the production side of the prosumer. And lastly, we cannot neglect the low voltage grid, which eventually serves as the source of energy if generation is low or generation is too high, and it also can absorb if the battery is full or out of operation or anything. So why would we have a prosumer, or why would we have an EMS as a prosumer? First of all, as we could see in the previous presentation or any other project, that these renewable energy sources are highly volatile and usually do not occur at the same time when the demand occurs. So PV production is high during the day, but load is higher during the evening when the people arrive. You have to charge the electrical vehicle. Heat demand is also higher when you are at home, of course. And this creates a mismatch between demand and supply. And there's a battery can help with that, but it needs some optimization. And given that your feed-in tariffs are usually much lower, compensated at a lower price than the actual grid price, this can actually end up in a financial problem for the prosumer. So increasing self-consumption through the battery in an optimizing manner is very important. So our objective was at the end to minimize this energy cost for the prosumer while keeping all the grid constraints like limits, not triggering any protection systems, also to ensure user comfort. The EV, the electrical vehicle, is fully charged by the end of the morning, so it can leave and departure. And also the temperature settings has to be fulfilled, as well as all the load demands of the prosumer at any given time. And the most important part of any working EMS is the optimization. And if you go through the literature, there are various numerous topics or methods, because it's getting a highly researched area over the past years. And there are loads of aspects which you have to look into if you want to optimize your system. And one of them is complexity, or you can look at the time of the optimization horizon, or the computational burden or feasibility. And without going into the details, we considered dynamic programming for our EMS implementation. And the reason for that is the great flexibility what it provides for us in terms of the objective functions or constraints which you can implement. It can be linear, nonlinear, convex, concave, any type of function. And it's also always provides you with an optimal solution, regardless of any scenario. It does not require a huge amount of data or historical knowledge on the system, or any prior knowledge like neural networks or genetic algorithms. But it has one flaw. Its computational burden is quite high, but with a reasonable optimization horizon and cleverly chosen parameters, this can easily overcome as well. So how it works? Basically, it breaks down the problem, the optimization problem, into sub-problems, and then solving those sub-problems backwards sequentially, it provides you with a global optimum, while also giving information on the sub-optimums as well. You have to divide the system into states and your process into stages. And by doing that, and going through the stages and with the selected states, you can end up with an optimum policy, it's called. But to further explain it and to connect it to our problem, you can look at this picture. And we define our states as SOC states of the battery and the vehicle, or the electrical vehicle. So we have two decision-making variables. And every stage, every time during the process can be represented by a two-dimensional matrix. And the matrix is made by these SOC values. So now the problem is that the EMS has to select a certain point at every stage, a certain state with two SOC values, which it goes through the whole process. And our goal is to minimize the electricity bill by the end of the process by going through the stages, while also keeping all the grid constraints and fulfilling all the load demands. And how well it works, we hopefully will prove its effectiveness in the next slides. And Shraddha, my colleague, is gonna take over from now.
Yeah, thanks. Hi, I'm Shraddha. So as Levente explained in the previous slides, that we have considered a rural household in Denmark to model this system. So it is important to size all of these assets before we dive into the optimization. So we have studied the different driving habits of the Danish cars, and also at what times these cars come home and at what times they leave from the house. And we have also looked into the residential EV charging setups. And we found out that the residential charging, it uses 11 kilowatt three-phase. So we have modeled it for that value. And the average size of a detached house in rural areas is approximately 150 square meters. So we considered that a 12 kilowatts of heat pump would be enough to comply with its heating needs. Also, there is a small wind turbine of 10 kilowatts in the backyard of the house. And we have modeled the electric vehicle with the same ratings and the same efficiency as a Tesla Model 3 Standard Plus. And the battery energy storage system has been experimented with 3 different values, namely 6.4 kilowatt hour, 10.52 kilowatt hour, and 11.52 kilowatt hours. And the rooftop PVs were sized to 6 kilowatts, as it is one of the most common used size here in Denmark. So depending on this, we have tried to construct a base case where we have not included any battery energy storage system or energy management system. And we have just studied how these components work without any supervision from this battery or an EMS. So basically, it follows the basic principle of power balance, and your loads are being supplied with the electricity which is bought from the grid, and also the electricity which is produced by the renewables. That's all. And the electric vehicle is charged as soon as it comes home and as soon as it is plugged into the plug-in station of the charging station. So in this case, the electric vehicle comes home at 17, which is 5 p.m. in the evening, and we can see a huge spike in the load around that time. So without EMS and without any optimization or battery, the yearly electricity cost for this setup is around 7,300 Danish kroners. So how do we formulate this setup using a dynamic programming? So we have tried to comply with some basic things such as a power balance equation. We have tried to set a maximum grid current limit, which has to be followed. We have tried to make sure that the battery power is limited within its maximum and minimum allowable discharge power within these transitions, as well as the battery SOC is limited within the transitions. We have tried to make sure that the electric vehicle power, which is maximum at 11 kilowatts, we have also tried to make sure that the temperature inside the house is maintained at a hospitable level, which is around the one set by the user. And also we have included the component of BESS degradation, which is the battery degradation. So the degradation or the damage which is caused to the battery with each of these transitions, it has been calculated over the year, and it has also been used as one of the parameters while calculating the function. And the objective function is built in order to reduce the electricity cost at the end of the year. So this is how the profiles look when we have applied this dynamic programming based optimization to the EMS. So the same day as the base case, which is a 24-hour frame from 9 a.m. to 9 a.m. is studied here. And we can see that the time is chosen as 9 a.m. because we want to show how the EV, the electric vehicle, is being scheduled. as the electric vehicle is supposed to leave the house at before 9 a.m. at around 7 a.m. in the morning. This small picture here shows the feed-in tariffs and the grid prices, the red one being the grid price and the blue one being the feed-in tariffs fetched from the Nord Pool. These are real-time electricity prices. Also, we can see here that around the night, these prices are really high. So the DP optimized EMS tries to use or dispatch the battery at that time so that we avoid buying electricity at a higher or more expensive rate. And it also schedules the electric vehicle to be charged when the prices are low, around 4 a.m. In the morning, so that we avoid buying electricity again at the expensive hours. So that's, and also at the end of the year, the electricity cost with this DP optimized EMS is 3,800 Danish kroners, which is almost half of that incurred without any EMS or a battery. So these are the exact battery power profiles for the same 24-hour duration and the corresponding SOC values of the battery for the 24-hour duration. So we have tried to, it is important to analyze the impact of the sizing of this battery and how much the SOC range can be, which is how much of the SOC values are permitted for the battery to swing within. So 3 different battery technologies were studied, namely 6.4, 10.5, and 11.5 kilowatt hour. And the installation costs of these batteries go up as their sizes go up, which is natural. And also the replacement cost for these batteries, once they are damaged, also go up as their size go up. So the damage or the degradation which is caused due to these batteries, due to the repeated use of them, it basically depends directly on how big of the SOC range they can cover, or how big of a SOC range they are allowed to operate within. So we have formulated some terms such as grid cost, which refers to the cost which is incurred only by trading electricity with the electricity grid. We have also coined a term called overall cost, which is the summation of this grid cost, which is the electricity traded cost, and the battery degradation cost. So some interesting plots were made based on these 3 costs for the different SOC ranges. So a SOC range of 1 here originally means that you're allowed to discharge the battery fully, which is 0%, and charge it to 100%. So your battery is allowed to take all these SOC values in between. And similarly, so it is observed that as you increase this SOC range, so as you allow the battery to use all of its capacity to charge and discharge, it is observed that the cost of degradation goes up, and the overall cost is going down, because the grid cost also goes down, because the fact that the battery has more flexibility to swing between higher values gives it advantage of lowering the overall electricity cost. But this trade-off between the degradation and the electricity bought, or the flexibility of this battery, can be seen here when a higher size of battery is used. So a local minima is obtained somewhere in the higher SOC ranges, where it says that it's more it's better to use the lower SOC ranges in order to optimize your cost. We are in the process right now to validate a sub part of this model that we have formulated, which uses only PV panels and a lithium-ion battery and loads in the laboratory. So in the lab, we have 3 kilowatts of PV power emulator, which is shown here, and it uses different technologies. It has different characteristics and different features such as cloud shading and etc. And it also has a 6.4 kilowatt lithium-ion battery. It has a grid inverter, which is 4 kilowatts. It has different programmable loads, and it controls and monitors using real-time MATLAB or Simulink interfaces. And our aim here is to implement this EMS here for the purpose of controlling the battery and the power flows. So to conclude shortly, we can say that it's really efficient to implement this D-based optimization. The costs at the end of the year have been reduced by almost 50% in overall. The EMS was really successful to comply with the constraints and to make sure that the electric vehicle is charged when it leaves the house, and the house temperature was maintained. So it provided the user comfort that we desired. And also it was interesting to observe the values of this SOC ranges against the cost or the degradation cost. And it was interesting to observe that at some ranges, it is outweighing the degradation cost. The grid cost outweighs the degradation cost. So that was all. And thank you for listening to us. And we would like to welcome any questions if you have them.
Well, thank you very much for a very interesting presentation. It is it's a thing which I'm sure will be needed for a lot of other countries as well in the future, where you have the possibility to be a prosumer. I'll let the first. I have a question for you. You said that this work is part of your thesis. Will the final document be available for the public? And you're welcome to send a link so that we can include it in the conference proceedings.
I think that at Aalborg University, the master theses are publicly available. So yes, we can send it when we finished.
Thank you very much. Well, are there questions or comments to Shraddha and Levente? Yes, Fritz, you have got a...
Yes, energy management systems in the Netherlands had more or less a false start. And that's because the gear that was on the market, the manufacturers of this gear were at the end salvation. So they were no longer on the market and there were no new software updates. Can you tell some more about the software you use, you are thinking to use? Is it open enough so that if manufacturers of measurement systems are going to insolvency, don't get this prosumers for a new investment?
Well, it's a bit disappointing in this regards because this is mainly research right now. So it was conducted mainly and quite fully in MATLAB, and also the laboratory setup is controlled through Simulink and MATLAB. So that's not publicly available and also not cheap. So I wouldn't say that based on MATLAB it can be possible, but I think that if the software, the code is done, I think it can be complied in any language, and then I think it's simple enough to implement anywhere. I hope so. That's why we use the dynamic programming also, because it doesn't require third-party softwares to solve like mixed integer linear programming, or these other ones usually require a solver program, but dynamic programming is simpler in this regard. It doesn't require a solver.
Thank you. I just wanted to make also a point.
Yeah.
Thank you very much.
We got two further questions. one from Henning Madsen and one from Mike Berge. Henning, I think you were the first one. Please unmute Henning.
Sorry.
Yeah, okay.
Now I'm have the mic on. This is my area, and I think Morten also lives in an area like this, and I think we could agree in many of the things, but one case is that we would probably include a water tank for storage of heat, for heat storage as well. Since we almost everybody in the countryside have the heat distributed by water, by radiators with water, we can have some benefit, and we have to have the consumption of water, also hot water for the household. So we can store some of the energy in as heat, and not rely solely on batteries to supply the heat at night, and so on.
Yes.
Have you considered making that kind of application? I know to operate with only one kind of storage, but have you considered this kind of system?
We have not considered it as of now, but yeah, it's an interesting input. Maybe we can think about it. Not right now, maybe because we have to finish the thesis along this. But
yes, actually, when we looked into heat pumps, then we found out that there are these two-in-one solutions, which are also having an electric boiler with a huge tank, and it can supply your hot water demand as well. The problem with that, it's a bit more demanding to model the hot water usage of a household than just the temperatures and just the overall general heat demand for room heating. So yes, it was looked at some point, but we neglected it for now because it would require more time than what we had.
Okay, thank you. And then I hope you have sufficient answer, Henning. Otherwise, we'll take it a bit later. Mike, you had a question.
Well, yes, first I just want to congratulate the both of you on an absolutely excellent project, and very timely with the emergence of more sophisticated power electronics. We're getting to the point where the electrical system of a home with wind and solar can be quite a complex energy balance and control situation. So your project provides some very interesting insights, and I'm looking forward to learning more. I would just comment that while I wouldn't change a thing about what you're doing, the market is actually much larger for people who aren't putting in more efficient HVAC and more efficient lighting in homes. The huge market, at least here in the US, is for people who have old-fashioned heating and cooling, inefficient windows. Maybe they've changed the lights, but they're going to be buying an electric car. They want to put in solar or wind or a combination, and they're willing to put in a larger solar and wind system rather than upgrading their HVAC system. They want, it's kind of a human flaw. They want to do one solution and then be done. You know, they don't want to do 12, even though the 12 is smarter. And so I think that's certainly the opportunity we see. because there are, of course, a lot more existing homes than there are brand new homes. And so I think that what you're doing is marvelous. You know, I'm going to try and copy some of it, actually.
Thank you. You are welcome to do so.
Okay, thank you. We'll have after the next presentation, we'll have have a discussion about the three matters, the three sessions, what are going on in the session 7 here. But I hope you'll stay there. And the idea is, instead of going to lunch immediately after, then go to the discussion afterward, it might be better that we take the discussion before the lunchtime or break. I hope that it will fit all of you and you can cope with it. Well, yes. Well, from what I can see from the other participants, it seems no problem. Thank you very much, both of you.